So welcome to this new video. So basically, I'll go over some basics of what I've done before, then quickly go over dot and cross products and try to give some interpretation about them. So basically, I did explain before that if you have a vector A, right, in component form is AI, EI, right, and if you try to expand that to get AI, EI, A1, E1 plus A2, E2 plus A3, E3. So these are the components of the vector A with respect to, so in case you see this next time, with respect to the basis EI, or that's E1, E2, and E3. So if you, let's make a quick sketch. You have this way. So you have this is a vector. It's called now let's call this X with a tilde below it. Actually, tilde is called a position vector. It's been defined with respect to its origin. Let's give this X, let's give here Y and here Z, right? So we have, if we have unit vectors in this direction, E1, another unit vector in this direction, E2, another unit vector in this direction, E3. Right. So this position vector can be defined as x e1 plus x e2. Sorry, this should be y because of this point here. Look at that, y plus z e3. So this is the position vector, and these are its components x1, x2, and x3. Of course, the vectors ei, they are all unit vectors, so the magnitude is 1. And this coordinate system we've just drawn here, this is the right hand orthogonal system. I hope that some sort of clears any discrepancies or anything. And now vectors, like vector, if you look at it, A is a vector, right? A is a vector. A is invariant. What that means is, let's assume A is in this space. This is A, right? A itself does not change. So A doesn't change, but its components change. So A is invariant, but its components change. What that means is the components, if you look at these components, they change with respect to the base vectors. So anytime you're defining it, you have to define with respect to base vectors. If this, for instance, this orthogonal system is being rotated at an angle, let's say it's an angle theta, something like this, theta maybe, for instance, then this E1 that lies here will come to this point, right? E2 will switch and all will all change. So at that point, the vector itself still remains the same, but its components have changed. I hope that clears things up. But let me remove this so that in case you get to see the PDF, you can understand basically what I was driving at. So A is invariant, it does not change, but its component change, and they change with respect to the basis vectors. So then, if you remember in the Einstein's summation convention, these are some of the things we've covered before, right? But I want to just make some things clear. So if the same index does not appear more than twice, that's the one rule we should know. Same index doesn't hmm, or more than twice or more than two times. Yeah, basic. So if you have A is your A, it's a matrix AI x k, that makes sense. If you have A I K B J K matrix multiplication, that still makes sense. If you have this times Aij, let's say if you multiply by j, so this is vector times matrix times vector. All these still make sense, right? All these three, they still make sense. But if you have something like this, you cannot have kk. Nah, that's wrong. Or you have something like k, b, k, k matrix, that's still wrong. Or you have something like x. So let me write this small x. So x, y, I. Unfortunately, this does not work. This is wrong, right? Because this appeared already. You're already stating this more than three times, more than two times, three times to this, free with this. So that does not work. Yeah. So one thing to note is free indices in each term of the equation or the equation or expression must be the same. So what's on the left hand side should be the same as what's on the right hand side, right? And the free indices or free index appears alone in a term. It appears alone in a term. It's not supposed to be doubled up or so. It's supposed to just appear alone in any particular term. So for instance, if you look at this AI plus BI equals to CI, this is tenable. If you have AI equals to AK, let's say I still, BKJ, I think then XJ, right? If you look at this very closely, you have an I here. By the time you are done with expressing all this, if you have this, right, you assume some of the J's and the K's out here. You have a K here, you have a KI here. This K in this case leaves you with an I remainder, which is equal to what you have on the left. I mean, it may look crude, but that gives you a visual understanding, right? So you have two I's, you can add the two I's to still give an I. So this is accepted. But if you have this xi ajk yk plus cj, now if you look at this well, you have an I here, right? So what it means that when you express everything here, you're supposed to get an I. But if you look at it, you have JK and K. These two K's, if you sum on them, you get just a J remaining. But we have a J plus a J to give you a J, but a J plus a J is not equal to an I. So this expression is wrong. I hope that clears things up. If you're looking at this again, if you look at this KJ, if you sum on the J's, you get a K, right? A K out. But you see KI with a K, you get an I remainder. And this I is equal to an I from the left hand side, which makes this terrible. But in this particular case, it reverses the case. I hope that makes and clears things up. Okay. So like I also previously explained, for dot product, let's assume A and B are vectors, right? Then what that means is A dot B is equal to the magnitude of A minus the magnitude of B cos theta is equal to B dot A. You have this, something like this. Let's assume here is B, let's say here is A, right? There's an angle between them. An angle between them, which is this, which we're interpreting to be this. So A dot B is equal to B dot A. How that makes sense? Now, if you have the norm gives you the notion of length. notion of length, right? Like distance. So if you're taking a linear algebra class, you can see the norm of values. So if you have a dot a, it's equal to ai dot ai, right? Now, if you want to find the dot product of this, looking at the expression we already have, we have a and a cos theta, right? Or let's say instead of saying cos theta, it's 0 because the angle between, if you have if here is a and a still falls on itself, right? The angle between the both is 0. So if you express this out, it gives this. Makes sense, right? Then this should be ai. Yeah, right. So this, so usually you can see this even in your linear algebra class. This is what we call the L2 norm. The L2 norm. Maybe in a subsequent video, I could just briefly talk about norms. So norms give you the notion of length, the length of a vector. If you want to find the length of a vector, then what you should be looking at is the norm of that vector. So for cross product, a cross b, right, is equal to a b sine theta. That is the main difference between dots. This was for dot product is cos, but for this is sine theta. Now let's try and give some interpretations about this basically. So if you have, let me sketch this out. You have a vector, you have a plane like this. I'll try to make my drawing as clear as possible. Okay, we have that. Plane doesn't look too good, but okay. You have a vector here. Let me use a different color just to make things look. You have A, you have a vector here, B, right? So if you look at this vector, of course, it spans the column space, right? There's this particular something like that. There's a span. Then there's a vector. This is C. Now, if you look at this closely, this one is perpendicular to this. This has perpendicular to this. Then this other one is perpendicular to this. That's B and C, perpendicular to this. So yeah, A and so A and B on A and B are perpendicular. Form an angle on this plane itself. A and C perpendicular. C and B also form one, two, right? So if you look at this angle, is theta on this plane. This is the plane itself, right? Yeah. So A cross B is equal to A B sine theta, well, based on what we have here. But in this case, we have a third vector, which is C, right? So we do what this will be C this to give you equal to C. So what I've just written now is this expression that says A cross B is equal to the magnitude of A times the magnitude of B sine theta, then times the unit vector. This is called the unit vector. This unit vector is normal to the plane, this plane. Unit vector is normal to this plane containing A and B in the direction defined by the right hand rule, right? So this is a unit vector. So what we've just written is A cross B is equal to C. And this expression is what is this, basically. I hope that makes sense. So this is a unit vector, and this unit vector is normal to the plane containing A and B in the direction defined by the right hand rule. That should be clear. Now, if you look at, let's look at C, right? C, you want to find C, it's simply A cross B all over the magnitude of A cross B. That is C. I hope that makes sense. Right. Okay. So, if we look at A cross B again, is equal to A equal to B sine theta equals to A. Look at it. This is A here. Here is B, right? It defines an area. It defines an area. If you look closely, it defines an area, which is this. I'm trying to color, right? Yes. So A cross B defines that area. So what it means that the area of that plane, basically, if you start the plane from here, then the area of the whole plane, or even from this part where we define the area of the plane, is magnitude of A and magnitude of B sine theta equals to A. So that is the area of the plane. And basically, you can use that to also define the area of that. I mean, yeah, that's an interpretation for that. Then you can still say A times N, right? If you remember what, we'll say A times N. Let's say N is like a unit vector up there, right? Maybe, or A, maybe like C or something. Let's say N here. So that will be A times B equal to, now, one thing I think I forgot to explain before is that anytime you are doing a cross product, that's where the permutation symbol comes into play, right? A times B, yeah. So the permutation symbol also can determine the sign for, even if we're doing cross products of unit vectors. So this will be permutation Kij AIBJEK, or if you prefer to write this with permutation IJK AIBJEK. I hope this makes sense to you, right? So this A times a unit, outward normal, or so it can be here or something this way, right? So this is an expression for it. So one last thing I think I should explain to make things very clear. Now, if you have, let's say you have three vectors. Let's draw this. This is one vector. This is another vector. Let's assume this is B. This is A. Let's assume this is, sorry. Assume this is C. C. So A, B, and C are all vectors. But the A, B, and C, one unique thing about them is that they are non-coplanar, meaning they don't lie in the same plane. One. Two, they are non-parallel to each other. Very important to note. Right? So if you look at it, so what this means is that if you look at B and A, B and A traces an area, right? Let's see if we can color that area off. B and A covers an area. Right. Let's assume there is a unit, there's an outward normal here, N. Now, so remember A, B, and C are not on the same plane. So let's if we draw, see, this is C, traces to cover that. This is, okay, let's do this. by looking at my sketch, you can see that I've been able to turn, or I've been able to form a volume by enclosing three vectors, which, if you remember, are still non-planar and non-coplanar and non-parallel, meaning they don't lie on the same plane and they're not parallel to each other. Right. Now, if you look at it, this area here, sorry, this area here, it's A cross B, right? That's the area. So let's say area. Let me give more room to that. Area is equal to this. This unit normal, right? It's like a unit vector, right? And you know what unit vectors? Unit vector to this plane A and spanned by A and B. So the unit vector n is equal to A cross B by the magnitude of A cross B. Right. Now, if you look at it very closely, you have this line, this, right? So from this point to this point, span a height. That is h, right? Yes, and h, this expression should be c. Dot. Okay, so this is the magnitude of the dot product of the vector c and the normal n, right? The volume enclosed by these three vectors now should be v equals to a times h. So we have an expression for a already, then it's h, right? So v equals to ah is equal to area a cross b, that's magnitude of it, times or cross c dot outward normal is already a times b all over a cross b, right? Equal to, now this one, we get rid of this, right? Sorry, not 0 but 1. Yep. To leave us with c dot a, right? So this is the volume enclosed by three vectors. Now this volume c dot a cross b is called the scalar triple product, and that's the volume enclosed by the three vectors, so it's called the scalar triple product. Hope that makes sense. So now c dot a cross b is equal to, now as I said earlier, anytime you have a cross product like this, you have to introduce the permutation symbol IJK. Pay attention to how I'm writing this closely. C, pick an I here. A, pick a J. B, pick a K. If you remember the earlier expressions, A cross B, A cross B, okay, it's did I write that out here? Okay, I've not written that out already. So the A cross B, the expressions for A cross B, basically, and adding C to it, right? A cross B would have simply been all of this without this. Yeah, okay. So this is the expression. And I mean, this still means you can still replace it with jki and it will still be the same. If you remember, if you follow ijk, the way we wrote, the naive method wrote it out, ijk is even permutation. You can still start with jki, still even with kij. So this can be I, kij, cij, bk. That still counts, that follows. You can still turn this to negative. In negative, then you can violate the order, right? This becomes j, I, k, c, I, a, j, b, k. If you violate it again, it can be I, k, j, c, I, a, j, b, k. Right? And you can violate it one more time to be k, j, I, c, I, a, j, b, k. I hope this makes sense. Right? So your scalar triple product A dot B cross C is equal to B dot C cross A equal to negative C dot B times A. Now we look at this A, B, C are vectors according to this order, right? So in this one, if you this is A, B, C, if you bring out if you start with B here, if you decide to start with the B here, you still follow the order. That's A, B, C, A, B, C, right? B, C, A. You can't, yeah, B, C, A. This expression still holds, but the moment you try to violate this by C, and instead of starting with A, you go to this, you interchange this, you introduce your negative sign, which is this. So one useful expression to understand, to know is this one as well. So I hope this video gives some good intuition and explanation on what the scalar vector product, I mean the vector product and dot product can do as well. So as a form of introduction, basically, I explained the components of a vector and the different components, and I explained that you referred or you describe the components of a vector with respect to its basis. So if you have a basis like at this point e1, e2, e3, if you decide to explain with respect to maybe it's an angle shift or so, yeah, this e1 moves to this part, so we have a different component, right? So these components can change. These components can change. They're invariant. They are variant, right? They change, but the vector itself does not change. So we've used that to describe a position vector. Position vector here. Let's describe this position vector, and for the vector A as well too, right? Then the Einstein summation convention. I just gave more examples based on what we've done in the previous videos. Yeah. So the same index does not appear more than twice, and for the free index on each term of the equation or each side of the equation must be the same. So if for instance you're getting an I here, I plus I, you get an I here. On the right hand side, you should get an I. Similarly here, if you're getting an I here, then on the right hand side, you should be getting an I too. And I explained it that this KJBJ, basically, what you can do is you summon the J's in this part here. You summon the J's. You summon the J's to get K, right? Kij, you summon the K's to get together I. So what's on the left will go to the right. But in this particular case, it's not the same. I hope that makes sense. The dot product, I also give an expression for the dot product, which is this, which I guess you're somewhat familiar with. Also, then explain the notion of norm. Norm simply means the length of a vector, gives you the notion of length. Cross product, A cross B, right? So the difference between this is that you have a sine theta in this one. Then I did try to explain, make some physical intuitions with that. Two vectors that span a plane. The area A times B, A cross B will give you C, right? And I explained the notion of a unit vector as well too. Unit vector, and I explained that. I got an expression for that, right? Then if you have a volume enclosed by three vectors, I think it's usually called a parallel pipe or so. So I explained that too and came out with an expression to find the volume, right? By finding we have the A, that's the area, and the height also. Then for the scalar triple product, this was basically like revision, just trying to show you the effect of different permutations. You see it changing the values, and when you decide to, if you violate the order, you flip the signs, you flip with a negative sign. Then the three variants of the scalar triple product. I hope you find this video useful. See you in the next video.